This equation is the first law of thermodynamics. Delta U is equal to Q plus W. Q is the heat transferred in the process and W is the work done. Now, because this is the PV work is the mechanical work, so we can write W as minus delta PV. Now the equation becomes delta U is equal to Q minus PV. Now if the process is carried out at constant pressure, then delta U is P delta V, because P is constant, only the volume will change. So delta U is Q P minus delta V. This subscript P is written here to indicate that the pressure is constant in the process. Now we can rearrange this equation as QP is equal to delta U plus P delta V. It's just the equation has been rearranged. Okay, now delta U is U2 minus U1. U2 is the internal energy of the final state and U1 is the internal energy of the initial state. So, and delta VE is the V2 minus V1. That is where V2 is the final volume and V1 is the initial volume. Therefore, QP is U2 minus U1 plus V2 minus V1. Okay, now this could be U2 and this P will be here, okay. U2 plus PV2 minus U1 plus PV1. Okay, now we define H as U plus PV. H is a new thermodynamic function which is defined by this relation U plus PV. Okay, now H is also a function of state but independent of the path by which the process has been carried, just like the function U, which is the internal energy, which is a function of the state but it is independent of the path. The change in internal energy is independent of the path. Similarly, delta H, the change in enthalpy, is independent of the path. Okay, now this equation becomes QP is equal to H2 minus H1. Okay, right? So we can write QP equal to delta H. For chemists, the enthalpy function is very important because delta H can directly be measured by measuring the heat transferred during a process which has been occurring at constant pressure. Right. In our lab, we perform experiments at constant pressure. And what is that constant pressure? It is the atmospheric pressure. Right. So here you see delta H is delta U plus P delta V. Now we can understand what enthalpy change is. Actually, enthalpy change, or you can also write this equation as QP as delta U plus P delta V. Now, the enthalpy change is the heat we measured minus the pressure volume work, right? So actually enthalpy is the corrected internal energy change. Of course, in our lab when we do the experiment, we just measure the heat evolved or heat absorbed, but not this particular term, which is of course the work. Alright, so this is it. Now we can say that in a constant pressure process, this is the energy lost. Energy lost. Okay, so now for example, NaOH aqueous plus HCl aqueous NaCl aqueous plus H2O liquid. The ionic reaction in this case is simply H plus OH minus H2O, right? Okay, this is aqueous. You can write, of course, aqueous, and this is liquid. So what you see here, this is an exothermic reaction. Exothermic reaction. And about 54 kilojoules of energy is released, right? So we put the minus sign because the heat transferred or the work produced is measured in the surroundings, right? So what we do in this case, that you take a calorimeter, right, which is fitted with a stirrer, and then there is a thermometer here. Now when you mix NaOH solution plus HCl aqueous, then the reaction takes place and the heat is absorbed. Heat is evolved. So that will rather warm the solution, and the temperature increase will be measured by this thermometer. So if T1 is the initial temperature and T2 is the final temperature, then the QP is delta H. QP is this minus the m, which is C into delta T, which is of course the amount of the solution which you have taken. Say if you may take 50 ml of HCl and 50 ml of sodium hydroxide, HCl 0.1 molar 50 and NaOH 50 ml and NaOH 0.1 molar, say 50 ml. Now your total volume is 100 ml, right? And we assume that the density of the solution is the same as that of water, 1 gram per ml, right? And we assume that the heat capacity of the solution is the same as that of water, which is 4.18 joules per degree Kelvin per mole. With this, we can calculate the heat released as minus 100 into 4.18 into, and suppose T2 minus T1 is say 1.8 degree centigrade. So this will be 1.8 degree centigrade. Okay. Right. So now therefore we can measure delta H as 100 minus 100 into 4.18 into 1.8 over the 0.1. Okay, so that will give you the delta H, the heat of neutralization. Now, okay, we know that delta U is Q plus W. Okay, right? And at constant pressure, at constant volume, W is delta PV is at constant volume delta PV is equal to, oh, okay, because there is no expansion of the gas when the volume is constant. So this will be P, okay, this will be 0. So at constant volume, delta U is simply QV. This V represents that the heat transferred is measured under the condition of constant volume. Similarly, because delta H is QP, that is the heat transferred under the condition of constant pressure is equal to the enthalpy change. Now we define heat capacity at constant pressure. And this is the given symbol Cp, right? Similarly, heat capacity at constant volume is given the symbol Cv. Right, so from what I have written there, Cp is delta H over delta T. Right, okay. And Cv is delta U over delta T. Right, or you can write that Cp is no, we can write here delta H is equal to Cp delta T. But if this here is per mole, Cp is the molar heat capacity at constant pressure per mole, and Cv is the molar heat capacity at constant volume per mole. Well, so if you have n mole, so you have to multiply by n Cp delta T. Similarly, delta U, you can write n Cv delta T. Right. So by these two equations, we can rather calculate the enthalpy change and the internal energy change. Okay. Now, after this, we come to enthalpy change in a reaction. Enthalpy change in a chemical reaction. Let us see. We have A moles of A plus B moles of B, giving you C moles of C plus D moles of D. So here delta H is the H enthalpy of products, which is, we can write summation minus enthalpy of reactants. Here P reactants. Right, so here. Now with this equation we can write delta H is equal to, because C moles of C, so HC plus D moles of D, so this for the product, minus A moles of A plus B moles of B. So this is the enthalpy change of the enthalpy change of the reaction. Okay. So now let us consider the a particular reaction, which is, for example, CH4 gas plus 2O2 gas gives you CO2 gas plus H2. How many H2? CO2 gas plus 2H2O liquid. 2H2O liquid. Now what you see here, now this is an example of combustion reaction. That is, CH4 is reacting with oxygen and producing carbon dioxide and water. It is an exothermic reaction, so delta H is equal to minus 890 kilojoule. So this delta H we can write as H right CO2 plus twice H2O minus minus CH4 plus HO2. Okay, now here you see that this is the enthalpy of carbon dioxide, then H2, the enthalpy of water, similarly the enthalpy of methane and oxygen. Absolute value of enthalpy of a compound we cannot measure. What we can measure, that the enthalpy change. Okay, so in a way, if you consider this is the initial state and this is the final state. So you produce the products from the reaction between the reactants. Okay, all right. So here, now here there are, because we need to compare enthalpy change of different reactions. So how can we do that? For that purpose, we have to define a reference scale. That means we should also consider that there should be some standard procedure to quote the enthalpy change of reaction. And what is that? That is considered standard state of compounds. Well, the standard state of compound is pressure is equal to 1 atmosphere and temperature is specified. But usually 25 degrees centigrade. This is the standard state of compounds. Similarly, the standard state of elements right, that is also pressure of 1 atmosphere and temperature which is specified, right? And but we usually take temperature 25 degrees centigrade. So this is the standard state of elements. Now standard state of solutions. The standard states of solution. So this is the pressure 1 atmosphere and concentration 1 molar. So I have given you the convention, and that is the standard state of all compounds is that pressure 1 atmosphere and temperature is specified, which is 25 degrees centigrade. And then for elements, again pressure 1 atmosphere and the temperature is specified, which is 25 degrees centigrade. And for solution, the pressure is 1 atmosphere and concentration is 1 molar. So now uh, enthalpy of elements in the standard state. What is the enthalpy of an element in the standard state? That is at pressure of 1 atmosphere at 25 degrees centigrade. So what we say that enthalpy of all elements in their most stable state at P is equal to 1 atmosphere and T is equal to 25 degrees centigrade, which is specified, is 0. For example, oxygen exists as O2. So the standard enthalpy of oxygen at 1 atmosphere pressure and 25 degrees centigrade is 0. Similarly, copper is an element which is in the solid form. It exists at a pressure of 1 atmosphere and 25 degrees centigrade as solid, that is the most stable form, and then the enthalpy of that is set equal to 0. Alright, now having done that, so now we can write for this reaction, if this reaction is carried out at 25 degrees centigrade, that is the products are at 25 degrees centigrade and 1 atmosphere pressure, and the reactants also at 25 degrees centigrade and 1 atmosphere pressure, then the enthalpy change is the standard enthalpy change of the reaction, right? So this superscript 0 means the pressure is 1 atmosphere, and the subscript 298 means the temperature is 298 degree Kelvin or 25 degree centigrade. So this is for pressure 1 atmosphere, and this is temperature, right? All right, so the standard enthalpy change of this reaction is minus 890 kJ, right? Okay, now let us consider the carbon. Carbon exists in different allotropic forms, for example, which are graphite, diamond, and buckyball. Now, most stable state of carbon is this one, most stable state. So, enthalpy of carbon as graphite at 25 degrees centigrade and 1 atmosphere pressure will be 0. Right, so, okay, now consider the reaction C, solid, graphite plus O2 gas, CO2 gas. Well, this is a very important reaction because the enthalpy change of this reaction is used in the calculation of enthalpy change of other reactions. So this is minus 393.5 kJ. Similarly, H2 gas plus half O2 gas, H2O liquid, and here delta H is minus 285.8 kJ. Right. Okay. So here you see both the reactions are exothermic because these are combustion reactions, and in these two reactions energy is liberated. Okay. All right. So we can write. Okay. This is delta H 298, and this is also delta H 298. Enthalpy of formation. Okay. Now we can write delta H naught 298 as H naught 298 this is H2O. Okay. H2O minus H naught 298 H2 plus half H naught 298 O2. Okay, so this is minus 890 kilojoule is equal to water is minus okay, formation of water. Delta H tonight is no sorry, sorry. I am writing for this reaction minus 285.8 is H naught 298 H2O minus 0 plus 0, because hydrogen is an element and oxygen is an element. Most stable state of hydrogen is H2 and most stable state of oxygen is O2. Right, so here we can write this is H naught 298 H2O. In other words, when 1 mole of water is produced from its elements hydrogen and oxygen in their most stable state at pressure of 1 atmosphere and 25 degrees centigrade temperature, then the enthalpy change is minus 285.8 kilojoule. Right. What does we write? So this we write that delta H naught F H2O is minus 285.8 kJ per mole, because 1 mole of water is formed from 1 mole of hydrogen and half a mole of oxygen. right? Similarly, delta H dot F CO3 carbon dioxide is minus 393.5 kg per mole. So now I can define a standard enthalpy of formation of compounds right. So we define it as enthalpy change of the reaction in which 1 mole of the compound is formed at 1 atmosphere pressure, T is equal to 25 degrees centigrade. When enthalpy change of the reaction in which 1 mole of the compound is formed at P is equal to 1 atmosphere and T is 25 degrees centigrade, from its elements in the most stable form also at P is equal to 1 atmosphere and T is equal to 25 degrees centigrade is called enthalpy of formation of the compound. This is the important definition of the enthalpy of formation of the compound. Standard enthalpy of formation of the compound. Okay, all right. So we have here now consider 6H6 C6H12O6. This is the formula for glucose, solid plus O2 gas giving you CO2 gas plus H2O liquid. Now let us write this is 6O2 and 6 carbon dioxide and 6 water. So this is the stoichiometric equation that is for the combustion of glucose. 1 mole of glucose when it is burnt in presence of oxygen, 6 moles of carbon dioxide in the gas form, and 6 moles of H2O are produced in the liquid form. Okay, now for this reaction, delta, what is delta H naught 298 of this reaction. This is what we have. Okay. Right, now the data is, this reaction is carried at 1 atmospheric pressure and 25 degree centigrade. So we have delta H naught F carbon dioxide 393.5 kJ, delta H dot F H2O, well, liquid, and this is gas, of course, is minus 285.8 kJ per mole, and delta H naught F C6 H12O6 is minus 1274.45 kJ per mole. Okay, so let us calculate what is the enthalpy change of the reaction. So here delta H naught 298 will be equal to these products, 6 minus 393.5 kilojoule, and then this 6 plus 6 minus 285.8. This is for the products, and then minus 1274.45 plus, now oxygen is in its standard state, 1 atmosphere pressure at 25 degrees centigrade, so its enthalpy of formation is 0. So here if we solve it, then we get 2801.69 kJ. This is the enthalpy change of the reaction which I have written up there. Okay. So now you can have all right, we can discuss one more example. I will rub it off. Problem. $50 ml of HCl, and that is 0.2 molar mixed with 50 ml of NaOH solution, 0.2 molar. Right. Okay. Then T initial is 22.2 degrees centigrade and TF is 23.5 degrees centigrade. Calculate delta H neutralization. Delta H neutralization. Okay. Well, as you know that this reaction is carried out in a calorimeter by mixing 50 ml of HCl with 50 ml of water, 50 ml of sodium hydroxide, both at 0.2 molar concentration. So the initial temperature of the solution was 22.2 degrees centigrade. On mixing, the final temperature rose 23.5 degree centigrade. So we have to calculate the heat of neutralization. You know that this reaction has been carried out in the laboratory at 1 atmospheric pressure. So P is constant. So what we measuring? We are measuring the enthalpy change of the reaction, right? Okay, so in this case, we have QP is equal to MC TF minus T1 or MC delta T. Right. Because assume that density of solution is 1.0 gram per ml and assume that the heat capacity of solution is 4.18 gram per ml. Right. Now delta T is 22.2 minus 23.5 is equal to minus 1.3 degrees centigrade. Now, right, so mass of 100 ml solution is 1 gram per ml into 100 ml is 100 gram. Right, so also therefore we have QP is equal to 100 gram into 4.18 joules per gram per degree centigrade into minus 1.3 degree centigrade. So this comes to be comes to be equal to minus 540 joules. Right, okay. Now, what we have that number of moles of H3O plus is equal to number of moles of HCl. Well, so we have 50, 0.5. We have also 50 ml is equal to 50 over 1000, which is equal to आएगा 0.05 liter. Okay, and concentration is 0.2 mole per liter. So the number of moles is equal to number of moles equal to 0.05 into 0.2 is equal to 0.10 mole. Right, it is 0.10 mole. Now, why is it 0.10 mole? Okay, 1, 2, 3. Okay, therefore, what we then have, delta H naught a 298 in this case is minus 540 joules over 0.010 mole, which is equal to minus 54 joules per mole or minus 54 kJ per mole. Right, so we end the lecture here.